All right. So, the first thing that we have on our agenda for the day is to look at steady state sinusoidal circuit analysis in the time domain. So there's going to be a point here within the next 3 or 4 minutes where legitimately I'm going to ask you guys not to take notes because the expectation is not that you will ever analyze a circuit in the way that I'm going to do it, because I'm trying to illustrate how terrible of an idea it is to analyze these circuits in the time domain. So I'll tell you when we get to the point of just participate and don't really worry about taking notes. So let's look at this real quick. So let's call this steady state sinusoidal circuit analysis. In the time domain. Okay, so before we jump into things here, I want us to make a couple of observations, okay? So today, for the most part, we are going to be analyzing what appears to be an incredibly simple circuit, okay? So I'm just going to have a current source in series with a resistor, and I'll give this a value here in just a moment, in series with an inductor. So let's just say, for the sake of argument, that this is a 10 ohm resistor, and this is going to be a 2 Henry inductor. I'm going to define the voltage drop across the resistor like so, the voltage drop across the inductor like so, and our single current that's flowing around here, our inductor current, like so. One last thing I'm going to do here is I'm going to define a voltage drop across my source. Okay. So let's start with a situation to where our source current, excuse me, IS, is simply a DC quantity. So let's say, just for the sake of argument, that it is 3 amps. Okay. So knowing that, could we determine the values for VR, VL, IL, and VS? So tell me what those are going to be. Let's start with VR. 30 volts. You got that just using Ohm's law, right? What about VL? What was that? It is 0, absolutely. So if the current flowing through the inductor doesn't change, then the voltage drop across the inductor is 0. Speaking of the inductor current, what's that? 3 amps. And lastly, what's our source voltage Vs? Do Kirchhoff's voltage law, right? So negative Vs plus Vr plus VL is equal to 0. So Vs is equal to Vr plus VL, or 30 volts. Okay, so what I'm trying to illustrate with this particular example is that when we put a DC signal as our input, we get DC signals as our output, where our output in this case could have been any of these quantities over here, right? All of these are different types of responses. It just depends on if we're interested in the resistor, interested and the inductor are interested in what the source is doing, but very obviously our excitation was DC and all of our responses were also DC. So in steady state sinusoidal circuit analysis, we're going to have something like this, okay? So let me draw this symbol a little better so you can see it, but effectively I'm just drawing the same regular current source and I'm putting a little tilde in the middle to let you guys know, hey, this is changing with time. So I'm going to call this IS of t. Once again, we're going to have our 10 ohm resistor, our 2 Henry inductor. The voltage drop across my resistor would be VR of t. The voltage drop across my inductor would be VL of t. And the voltage drop across my source would be Vs of t. And the current flowing around that loop would be IL of t. So for a steady state sinusoidal signal, we are going to say that IS of t, let's make that 3 cosine 8t plus 0 degrees amps. So I'm explicitly choosing a phase angle of 0 degrees here. I just want to mention it, okay? So when we had a DC excitation source, we got DC responses. So it stands to reason that when we have a sinusoidal excitation source, we should have sinusoidal responses, okay? So I'm going to venture a guess that my source voltage Vs of t will be able to be represented in a form V naught cosine 8t plus some phase angle theta V volts. And what we're going to spend the next several minutes doing is proving that that is true, okay? So this is the part where we have to suffer through a whole bunch of math that, again, I am expecting you guys to never, ever have to do on your own. I will talk to you about shortcuts and all of that kind of stuff here in a moment. So this is just us kind of freestyling with some trig and algebra and all that kind of stuff for the next several minutes. And I'm going to use Desmos to help us out as well, okay? So I believe that I could write a Kirchhoff's voltage law equation to find my source voltage Vs of t, and this would be nothing more than the sum of my resistor voltage and my inductor voltage, like so. Does anybody have a problem with this Kirchhoff's voltage law expression? Fairly straightforward, okay? So now let's take a moment and figure out what VR of t and VL of t will be, okay? So how are we going to find VR of t? We're going to use Ohm's law, literally just like we did a couple of minutes ago for that DC circuit, right? So that's just going to be R times IS of t. So that's going to look like 10 ohms times 3 cosine 8t plus 0 degrees amps. And so that's going to give me 30 cosine 8t plus 0 degrees volts. Nothing particularly wild or crazy there, right? For our inductor voltage, things are going to get a little bit more difficult because we have a calculus-based relationship, right? So the voltage drop across an inductor is given by L times the derivative of the inductor current, which is just IS of t in this case. So that's going to look like 2 henries, where a henry is a volt second per ampere, times the derivative of that 3 cosine 8t plus 0 degrees amps. So how do I take the derivative of a cosine function? Remind me, I'm an old man. So we're going to have, so the derivative of cosine is negative sine, but we're also going to have to apply the chain rule and pull out that 8 radians per second. So I'm just going to have negative 8 radians per second. I'm going to go ahead and pull out the 3 amps as well. And now I should have sine of 8t plus 0 degrees. And if we look at our units just really quickly, we have amps in the denominator is canceled by amps in the numerator. Seconds in the numerator is canceled by seconds in the denominator. Radians are a dimensionless quantity, so I can pretty much just throw those away and I just get a voltage. So putting things together, 2 times negative 8 is negative 16, times 3 is negative 48, sine 8t plus 0 degrees volts. And so putting these two things together, we find that our source voltage is going to be 30 cosine 8t plus 0 degrees minus 48 sine 8t plus 0 degrees volts. So that in and of itself wasn't particularly difficult. But I want you guys to notice that right now, our result is not a single sinusoidal function like we would expect. It is a combination of sinusoids. So there should be a more compact form. And to prove this to you, I'm going to plot these two things on Desmos really quickly. So here we go. So for my first signal, I don't have caps lock on, sorry. V1 of x, that was 30 cosine 8t, and, oh, excuse me, 8x. Let me go into my settings here so that this is slightly less horrifying. So let's make this negative 50 and this positive 50. And let's make this negative 1 and positive 1 so that we have a nice, pretty sinusoidal signal. Okay. So that's my voltage drop across my resistor. The voltage drop across my inductor was negative 48 sine 8x, right? And if I add V1 and V2 together, let me expand this out just a smidge so that we can see it. And let me just turn these off. I can see that this looks like a sinusoid, right? It's a sinusoid that appears to have a positive phase angle if I'm expressing it as a cosine function, because it's shifted to the left by some amount. It has a peak value in the ballpark of something like 58. We can click on it here, 56.603, and we could actually use that value right there to calculate what our phase angle is. But we're not always going to have the luxury of a laptop where we can graph stuff in front of us, so we probably need to figure out a different way. And that different way involves the use of several trig identities. Okay. So let's talk about what that is going to entail. So I have accidentally made this slightly easier than I intended by giving us a phase angle to start with of 0 degrees. So this will be a little less horrifying than usual, but let's look at a couple of things, right? So our expectation is that Vs of t is going to be of the form Vm cosine, I'm going to put 8t here, where 8 is just our angular frequency omega, plus some theta v. That is one of those trig identities where we have the cosine of alpha plus beta, right? So that means that I could express this as Vm times cosine alpha, which in this case is going to be 8t, cosine of beta, which will be theta v, minus the sine of alpha, 8t, times the sine of beta, theta v. So I already kind of sort of have it in this form, right? So I can see that I have some magnitude times a cosine function with a phase angle of 0, and then some magnitude times a sine function with a phase angle of 0, okay? So realistically, what we need to do is just figure out how to relate these two things using our knowledge of trig and stuff like that to figure it out, okay? So sorry, now I'm trying to remember exactly how we do this. So let me think about this real quickly. Well, oh, actually, no, it's rather easy. So effectively, what we've got is that Vm times the cosine of theta v has to equal 30 volts. Because we have cosine of 8t plus 0 degrees here, so this 30 has to be effectively what's left. So that's just Vm times cosine of theta v. We already have a minus sign in the middle there, so we're good on that side of things. So that means that Vm sine of theta v must be equal to 48 volts. Okay. And so we can use these two pieces of information to determine what Vm and theta v are, right? So for example, we know that if I did Vm times cosine of theta v quantity squared plus Vm of sine theta v quantity squared, that's the same thing as Vm squared times cosine squared theta v plus sine squared theta v. Well, what's cosine squared plus sine squared theta v? 1, right? Cosine squared plus sine squared of the same angle is 1, absolutely. So this whole thing right here goes to 1, and from that, we could say that our magnitude Vm is just the square root of Vm cosine theta v quantity squared plus Vm sine theta v quantity squared, which is literally just the square root of 30 volts squared plus 48 volts squared. And if I put this into my calculator, I get 56.604 volts. So how well does that compare to what we were expecting from Desmos? I think it's pretty spot on. Okay. For our phase angle, so I know that the tangent of theta v is equal to sine of theta v over the cosine of theta v. That's how we define a tangent function, right? Does anything change if I put a Vm in front of both terms? Absolutely not, right? Because those guys are just going to cancel each other out. And so I could say then that our phase angle, theta v, is just the inverse tangent of Vm sine theta v over Vm cosine theta v, or the inverse tangent of 48 over 30. So if I do the arctangent of 48 over 30, I get positive 57.995 degrees. So putting these two things together, Vs of t seems to be 56.604 times the cosine of 8t plus 57.995 degrees volts. So let's throw this into Desmos and see if we're right. So 56.604 cosine 8x plus 57.995. And then I need to make sure that I have this as a radian angle. So pi over 180 gives me this purple curve. So what happened to the green curve that represented the sum of the resistor voltage and the sum of the inductor voltage? It's underneath the purple curve because we've matched it so exactly we literally can't even see it anymore, right? So if I turn this guy off, we're spot on. Okay. Now this example was relatively easy because I accidentally decided not to be a dick today and give us a phase angle that wasn't zero that would make this take another 10 minutes or so. Okay. That being said, we still spent the better part of 25 minutes or so doing this incredibly simple circuit that contains a whopping 2 elements in series with a source, right? So we have this thing up here. We solved it in the time domain, and it took a gross amount of time, in my opinion. So what I want us to do now is to see if we can make this easier using complex numbers, okay? So I'm going to start from this point right here, where we have 30 cosine 8t minus 48 sine 8t. Let's just come down here as an alternative method. So Vs of t is 30 cosine 8t plus 0 degrees minus 48 sine 8t plus 0 degrees volts. Okay. And so what I'm going to do is I'm going to make an educated guess. So my signal 30 cosine 8t plus 0 degrees has a magnitude, an angular frequency, and a phase angle. A complex number in exponential form has a magnitude, an angular frequency, and a phase angle. So what if I called this 30 cosine, nope, not cosine, I'm getting away from that, my apologies, 30 e to the j 8t plus 0 degrees. And this guy over here, I need to switch it to be a cosine function so that we are comparing them similarly. So what's 48 sine 8t plus 0 degrees going to look like as a cosine function? So we just subtract 90 degrees, right? So that would be 48 e to the j 8t minus 90 degrees. Now, because I'm dealing with complex numbers, I think my Vs of t on the left-hand side should probably look like Vm e to the j 8t plus theta v now, okay? And because of the way that exponential functions work, I actually have a common factor of e to the j 8t on both sides that I can actually just throw away, okay? So we would have Vm e to the j theta v is equal to 30 e to the j 0 degrees minus 48 e to the negative j 90 degrees. Well, our calculators can't handle exponential form complex numbers, but they can handle polar form complex numbers. So I might call this 30 angle 0 degrees minus 48 angle negative 90 degrees. And that's something that we can literally just put in our calculator. So I want you guys to please put that into your calculator and tell me what you get. And I would like the answer in both rectangular form and polar form, please. What'd you get, Ashton? 30 plus J 48, okay? So we literally got the exact same magnitude and the exact same phase angle by using these complex numbers, but we got there much, much quicker, okay? So what we're going to spend the rest of our time today on is developing a more formal approach that will work for literally every circuit that we could see instead of just this one circuit, okay? Before we do that, though, I want to bring you guys' attention to some of the web work problems from homework 19, okay? Because you're asked to do a bunch of things, and it seems like the expectation is for you guys to suffer through trig identities and whatnot, and I'm going to tell you very bluntly that you can do it with complex numbers about 100 times faster. And so I want to make sure that we all understand what's going on here. So let's look at WebWork set number 19. And let's see which problem it is that I'm interested in. Nope, we looked at that one the other day. So let's move on to this guy right here. Okay. So for this particular problem, we are asked to find A, B, C, and our phase angle if 52 cosine 100t minus 119 degrees minus 10 sine 100t plus 77 degrees is equal to that thing. So I'm just going to write this stuff down real quick. Okay. So, sorry, I have the memory of a goldfish. 52 cosine 100t minus 119 degrees. Minus 10 sine 100t plus 77 degrees. 10 sine 100 plus 77. And we were told that it is equal to A cosine 100t, if I'm not mistaken, plus B, but let me double check there. Yep, plus B sine 100t. And also it's equal to C cosine 100t plus some phase angle phi. Okay. So let's use the trick that we just figured out real quick to figure out what C and our phase angle is, right? So how would I represent this 52 cosine 100t minus 119 degrees as a complex number? And let's go ahead and skip the step of bothering with the omega t part because we know we're going to throw that away. And I'll explain why we get to throw it away here in a couple of minutes. Okay. So I think this is just 52 angle negative 119, right? So how is that any different than what we just did right here? Nothing different. We took the magnitude, we took the phase angle, we threw the rest away. What about this 10 sine 100t plus 77? So a moment ago, we converted it into a cosine function first. So that would be 10 cosine 100t minus 13 degrees, if my mental math is correct. What would that look like as a polar form complex number? What's that? 10 angle negative 13, and then I'll put a minus sign there. So throw this into your calculator and give me the answer in both polar form and rectangular form. What was that again? 43.23. Okay, so that's the rectangular form. $55.594. negative 128.957 degrees. All right. So effectively, or not effectively, exactly actually, this number right here is C. This number right here is phi. This number right here is A. And this number right here, without the J, I want to be clear, is actually negative B. And the reason it's negative B is because of how that trig identity works. Cosine of alpha plus beta is equal to cosine alpha cosine beta minus sine alpha sine beta. Yep, so let's check it out. Find my cursor here. So what was A again? Because I can't remember shit. Negative 34.593. Not 59. Is that right? Okay. What's B gonna be? All right. Caroline hit me with C and phi again. Oh my God, you're talking at the same time. I feel like shit and I can't understand anything. I had an extra 5 in there. Okay. There we go. So complex numbers means we can do this stuff in seconds, and it would take us several minutes to do it using trig identities, okay? So complex numbers are an incredibly powerful tool to have at our disposal when we're going to be manipulating sinusoidal signals, which is all we're going to be doing for the rest of this class, okay? So I just wanted to give you guys a heads up on the much, much easier way to do this particular homework set. Instead of suffering through a shitload of trig, use complex numbers and knock it out in moments, okay? All right, so now let's get into what I believe is the fun part of this and you guys hate. Why does this work? Okay. So let's say that I have a linear black box network. My input terminals are over here on the left. My output terminals are over here on the right, okay? So if I apply some sort of sinusoidal excitation signal, does not matter whether or it is a voltage or a current. I'm just going to call this x1 of t, like so. And I measure some output, y1 of t. Again, it could be a voltage or a current. What we just found is that when x1 of t is of the form x naught cosine omega t plus some phase angle theta, our output will be of the form y naught cosine omega t plus some different phase angle. We literally proved this when we did that exercise. Okay. Let's say that I take that exact same linear black box network and I excite it sinusoidally as well with a signal x2 of t. I should be able to observe some output signal, y2 of t. And let's say that in this particular case, x2 of t was x naught sine omega t plus some phase angle theta. What would we expect our output to be? So when we put DC in, we got DC out. When we put a cosine function in, we got a cosine function out. So what happens when we put a sine function in? We get a sine function out. And that should be very easy to understand because we know that a cosine function and a sine function are literally the same thing. They're just shifted versions of each other. So let's use the scaling or homogeneity property of linearity really quickly, right? So for those of you that don't remember this, because this was way back in lecture number 6 or 7, so it's been quite a while, the scaling or homogeneity property of linearity tells us that if we scale our input by an arbitrary constant factor, our output is scaled by that same arbitrary constant factor. Well, wouldn't you know it, J is an arbitrary constant factor that we can scale things by. So if I scale my input by a factor of J, it should scale my output by that same factor of J. Okay. So lastly, let's take our same black box linear network and excite it with a combination of those signals. So this will be x of t at our input. This will be y of t at our output. And x of t is just going to be x1 plus x2, which looks like x naught cosine omega t plus theta plus j x naught sine omega t plus theta. And if you remember our trig identity called Euler's identity from last class meeting, that is simply x naught e to the j omega t plus theta. Or if you remember how we convert from rectangular form complex numbers to exponential form complex numbers, it's the exact same relationship. That is literally just Euler's identity in application. Okay. So if I have that cosine function plus j sine function, and I add those signals together, that is the exact same thing as me applying a complex exponential excitation. Now, when we look at our output signal, y of t, we would simply have y1 plus y2. So that would be y naught cosine omega t plus phi plus j y naught cosine omega t plus phi. And we could add those together to make a complex number as well, but I'm not going to, okay? So the reason I'm not going to is because I want us to make an observation. The real part of our input signal gives us the real part of our output signal. So effectively, if we convert any sinusoidal excitation into a complex number, use the complex numbers to do the math, and then only take the real part of that result, it will give us the same exact answer as if we had done everything using a combination of trig and calculus. So complex numbers effectively turn trigonometry and calculus in the time domain into algebra in what we're going to call the frequency domain. And that's how we are going to analyze every circuit from here on out. We're going to use the frequency domain because it makes the math wildly easier. So let's now talk about frequency domain analysis, or sinusoidal steady state analysis. In the frequency domain. So the first concept that I am going to introduce is what is called phasor representation of voltage and current signals. And technically, we've already done this twice at this point, okay? So I'm going to go through this relatively quickly, okay? So let's say that I have a voltage signal, V of t, is equal to Vm cosine omega t plus theta v. And I have a current waveform of the form Im cosine omega t plus theta I. These are my time domain signals. We just learned that this is the real part of the complex number Vm e to the j omega t plus theta v. And our current waveform is the real part of the complex signal Im e to the j omega t plus theta I. Well, these guys right here are what I'm going to call, for lack of a better term, our mixed domain signals. Okay. And what I mean by that is effectively they are just an intermediate step between the time domain and what we're going to call the frequency or phasor domain, okay? So over here to the right-hand side, I'm now going to introduce our frequency domain signals, okay? And these are what we call our voltage and current phasors, where, for what it's worth, the word phasor is just a portmanteau of the words phase vector, okay? So our voltage phasor V, I'm going to use a capital letter here, and I'm putting a bar over it. So this is telling you guys, hey, expect a complex number. So this is literally just going to be the magnitude and the phase angle, and we throw everything else away, which is literally exactly what we did a couple of moments ago to do the math that we were doing. And our phase current, or our phasor current I, is just going to be Im angle theta I. So these are our phasors, and they are also known as frequency domain signals. So when we have a voltage or current in the time domain, and we want to convert it into the frequency domain, we simply make sure that we're working with a cosine function, take the magnitude, take the phase angle, throw the rest away. None of the other parts matter. Okay? So just as a quick example, even though we've already done this a couple of times, let's say that I have some voltage VA of t that is 8 cosine 77t plus 15 degrees volts. What would my phasor representation of this signal be? Why haven't you told me the answer yet? 8 angle 15. If I had VB was 12 sine 77t plus 60 degrees, what would my phasor be? 12 angle negative 30 degrees volts. Connor, why is the phase angle negative 30 degrees? Because we had to change our sine function to a cosine function. If I had something like VC was 6 cosine 15t plus 12 degrees minus 8 sine 15t plus 45 degrees volts, how would I handle that? So I'd change this to 6 cosine 15t plus 12 degrees minus 8 cosine 15t minus 45 degrees. And then that means that our phasor voltage VC would simply be 6 angle 12 degrees minus 8 angle negative 45 degrees. Putting that into my calculator, 6 angle 12 minus 8 angle negative 45 gives me 6.908 with an angle of 88.241 degrees. So we combine those sinusoids effectively in the frequency domain because the math is much easier. All right, so before I move on from here, are you all catching what I'm throwing with regards to phasors? This should be the easiest part of your day. Okay. Keep the magnitude, convert our signal to a cosine function, keep the magnitude, keep the phase angle, throw the rest away. All right, so now let's talk about frequency domain relationships for resistors, inductors, and capacitors. Okay. So let's start with a simple resistor. So here I have some resistance R, and I'm going to define the voltage drop across my resistor V of t like so, and the current I of t as flowing into the positive polarity terminal. And we are going to say that V of t is Vm cosine omega t plus theta v, which, as a reminder, is just the real part of Vm e to the j omega t plus theta v. And our current should have that same basic form. So Im cosine omega t plus theta I, which is the real part of Im e to the j omega t plus theta I, like so. So for a resistor, what's the relationship between current and voltage? Ohm's law. So V of t is equal to R times I of t. So all I'm going to do here to figure out how this circuit element behaves in the frequency domain is I'm going to substitute in my mixed domain signals, okay? So that means that I'm going to have on the left-hand side, Vm e to the j omega t plus theta v is going to be equal to R times Im e to the j omega t plus theta I. Just simple, direct substitution, okay? Now, several minutes ago at this point, I said that we had a common factor of e to the j omega t on both sides. I'm going to show you that explicitly here, right? So I could write my left-hand side as Vm e to the j omega t times e to the j theta v. Are we okay with me splitting up my exponential into two smaller parts? Okay. And on the right-hand side, I'm going to do the exact same thing. So e to the j omega t times e to the j theta I. And now we can very obviously see that there is an e to the j omega t on both sides of the equal sign. And so if I throw that information away, which is what I do to form my phasors, it changes nothing about the relationship between the left-hand side of the equal sign and the right-hand side of the equal sign. So what do I have on the left-hand side here? I have a polar form complex number, right? I have a magnitude e to the j phase angle. On the right-hand side, I have a polar form complex number where my magnitude is R times Im and my phase angle is theta I. So I can infer from this relationship a couple of things, okay? The magnitude on the left-hand side, Vm, has to equal to the magnitude on the right-hand side, R times Im. The phase angle on the left-hand side, theta v, has to equal to the phase angle on the right-hand side, which is theta I. So effectively, a resistor does not introduce any phase delay or advancement in our system. The phase of the voltage drop across a resistor is the same as the phase of the current flowing through the resistor, okay? So let me just come down one step here. So Vm e to the j theta v is equal to R times Im e to the j theta I. So what if I wrote these exponential form complex numbers in polar form? Well, I would have Vm angle theta v is equal to R times Im angle theta I. Vm angle theta v is literally the definition of my voltage phasor. And Im angle theta I is the definition of my current phasor. So effectively, what we have just learned is that Ohm's law in the frequency domain is the same damn thing as Ohm's law in the time domain. Ohm's law is always Ohm's law. That's why it's a law. So this is probably the most boring of the results, but it is very important. We treat resistors in the frequency domain exactly the same as we treat them in the time domain. The math bears out. So before we move on from this, I do want to make a note. These relationships over here are important, and we are going to see them crop up over and over and over again. Okay. So just kind of have in the back of your mind that the phase angle of the voltage for a resistor is always going to be equal to the phase angle of the current. The magnitude of the voltage is just R times the magnitude of the current. Okay. So now let's look at an inductor. So I have some inductor L. Here's my voltage V of t. Here's my current I of t. And I'm going to apply the exact same voltage and current effectively. Okay. So V of t will be Vm cosine omega t plus theta v, which is nothing more than the real part of Vm e to the j omega t plus theta v. And I of t is equal to Im cosine omega t plus theta I, which is the real part of Im e to the j omega t plus theta I. So what's the relationship between current and voltage in an inductor? And we're going to use the derivative-based relationship because it makes the math much easier. And also, I hate integrals. So what's the relationship? We used it earlier today. So V is L di by dt. Absolutely right. And so we're just going to substitute that in. So on the left-hand side, we will have Vm e to the j omega t plus theta v will be equal to L times the derivative with respect to time of Im e to the j omega t plus theta I. So let's perform that derivative. What's the derivative of Im e to the j omega t plus theta I with respect to t? It's going to be j omega times the original expression. Absolutely right. So this is going to reduce down to j omega L times Im e to the j omega t plus theta I. So I'm going to do some manipulation of this thing, okay? So over here, I'm going to have Vm e to the j omega t e to the j theta v. Here I'll have j omega L times Im e to the j omega t e to the j theta I. And we can see very easily that the e to the j omega t's cancel each other out. So I've got something kind of interesting going on here. So let me explain what I mean by that specifically. So on the left-hand side, I have a simple polar form complex number, right? I have a Vm e to the j theta v. On the right-hand side, I have a rectangular form complex number being multiplied by a polar form complex number. So really, what I want to do is figure out what the hell to do with that j, because if I can get that j out, then it's going to look like a polar form complex number. So I want to make you guys aware of something. So this is a quick-ish tangent, so I'm going to do this like on the last page, and then we'll go back to things. So what I'm doing here is I'm just drawing a complex plane, okay, where this is my real axis and this is my imaginary axis. So if I go out 1 unit in the real direction, what we would conventionally call the number 1, in rectangular form, we would call that 1 plus j0. And in exponential form, that would look like 1e to the j 0 degrees. And in polar form, that would look like 1 angle 0 degrees. If I go up 1 unit in the imaginary direction, what we would normally call j, in rectangular form is 0 plus j1. In exponential form, it's 1e to the j 90 degrees. And in polar form, it's 1 angle positive 90 degrees. If I go out 1 unit in the negative direction, we would normally call that -1. In rectangular form, that's going to look like -1 plus j0. Or in exponential form, 1e to the plus or minus j 180 degrees. Or in polar form, 1 angle plus or minus 180 degrees. And lastly, if I go down 1 unit in the imaginary direction, we would normally call that -j, or 0 minus j1, or 1 angle, 1e to the j -90 degrees, or 1 angle minus 90 degrees. So effectively, anywhere I see j, I can just replace it with e to the j 90 degrees. So I'm going to go back up and I'm going to do that really quickly. So this would be the same thing as omega L times Im, e to the j omega t, e to the j theta I, plus 90 degrees. Because if I multiply e to the j theta I times e to the j 90 degrees, I can just add those together. And then this guy cancels out. So what we can observe from here, now that I have, yes, Kaylee. The only L is the L from up front. So we now have an exponential form complex number on the left-hand side and an exponential form complex number on the right-hand side. So we can see that the magnitude of our voltage is simply equal to omega L times Im, and we can see that our phase angle, theta V, is equal to theta I plus 90 degrees. So if we look at this phase angle thing, what observation can we make? Well, theta V is always 90 degrees more positive than theta I. So our voltage is always leading our current by 90 degrees, or our current is always lagging our voltage by 90 degrees. I'm going to write that down because that's something important. All right. So let's go back to more of the left-hand side of things, okay? So Vm e to the j theta V could be expressed in polar form as Vm angle theta V. And we would have j omega L times Im angle theta I over here. Since Vm angle theta V is by definition our phasor voltage, we have the relationship phasor voltage V is equal to j omega L times phasor current I for an inductor. So this is how current and voltage across an inductor are related in the frequency domain. Lastly, we have capacitors. I promise things will get slightly less boring here shortly. So what's the relationship between current and voltage in a capacitor? Derivative based, please. So the current in the capacitor is equal to C times the derivative of the voltage drop across the capacitor. So this relationship is incredibly similar to what we just saw with the inductors, but the current and voltage have switched place, and everywhere we saw an L, we should have a C. So we can pretty much skip ahead. So what we would have, this would be Im e to the j omega t plus theta I is equal to C times the derivative with respect to time of, Vm e to the j omega t plus theta v. Skipping ahead several steps, what we wind up getting is Im e to the j theta I will be equal to j omega c times Vm e to the j theta v, or omega c Vm e to the j theta v plus 90 degrees. So we can see that Im is equal to omega c times Vm, and theta I is equal to theta v plus 90 degrees. So in a capacitor, the current is always leading the voltage by exactly 90 degrees. And then lastly, putting things in terms of our phasor relationships, this looks like Im angle theta I is equal to j omega c times Vm angle theta v, or our phasor current I is equal to j omega c times our phasor voltage V. So these are our frequency domain relationships for voltage and current for all of the components that we're used to dealing with: resistors, inductors, and capacitors. So we are incredibly close to being able to analyze circuits entirely in the frequency domain. There's just one last little thing that we need to put together, okay? Am I good to start another page of notes here? If you need a moment to catch up, please. Yeah. We all good to go? Okay. So my last small topic for today, before we literally tie all of this together, and I show you how we could have analyzed that circuit from the beginning of the class with literally a single equation, is the concept of impedance. So we're going to go way back to the third day of class when we learned Ohm's law for this one, okay? So I hope you guys can recall, because we've done this multiple times at this point, that whenever I have a linear black box network So when I excited this network with a DC signal, doesn't matter whether it's a current or a voltage, when I measured the voltage drop across the terminals of the device and I measured the DC current flowing into the device, we defined the resistance R as the ratio of voltage to current. Okay. So if I take that same linear black box network and I sinusoidally excite it, doesn't matter if I apply a sinusoidal voltage or a sinusoidal current. If I measure the phasor voltage across the terminals of the network and the phasor current flowing into the network, I get what's called the impedance Z, where Z is just the ratio of the phasor voltage to the phasor current. So it is effectively playing the role that resistance did in DC circuits. Okay. Now, our impedance is a ratio of complex numbers, which means it is also a complex number. Okay. So that means that we are going to have a polar form, and we'll have special parts there, and then we'll have a rectangular form as well. Okay, so let's start with our polar form representation. So phasor voltage V is just Vm angle theta V, and phasor current I is just Im angle theta I. We learned in class on Wednesday that when I'm dividing two complex numbers in the polar form, this simply results in the magnitude the magnitude of the numerator divided by the magnitude of the denominator with an angle that is the difference. So this is our magnitude of our impedance and the angle of our impedance. Okay, so the angle of the impedance is just theta V minus theta I, and that is another thing that's going to crop up over and over and over again. So there's our polar form, and I think it's a little bit boring, but we do use it, okay? In rectangular form, what we have is R plus JX, where R the real part is the resistance and X, the imaginary part, is what we call our reactance. So resistance is the real part, reactance is the imaginary part, and because we have a polar form representation and a rectangular form representation, we can use the relationships that we learned in class on Wednesday to go back and forth between these two forms, or more realistically, we can just press the button on our calculator to make it do it for us. Okay. So let's take these definitions for impedance and let's look at what we have for our resistors, inductors, and capacitors. Okay. So for a resistor, our impedance Z subscript R, again, is just going to be the ratio of the voltage phasor over the current phasor. So I want you guys to scroll up into your notes and tell me what the ratio of V phasor over I phasor should be. Hmm? Yeah. So just to be clear, I have this relationship right here. I'm just dividing both sides of the expression by I. So what do I get when I move the I from the right-hand side over to the left-hand side? Because I'm just looking for V over I. R. So the impedance of a resistor is just the resistor value itself. Okay? More formally, in the rectangular form, this is going to look like R plus J0. And in polar form, this is going to look like R angle 0 degrees. Okay. So what are the units of the impedance of a resistor? Ohms, because it's just the resistor value itself. All right. Now let's look at an inductor. So going back in our notes, what should V over I be for an inductor? J omega L. So in rectangular form, this is going to look like 0 plus J omega L. And in polar form, this is going to look like omega L with an angle of 90 degrees. Let's look at our units here really quickly, right? So omega is in radians per second. And then inductance, Henry, is a volt second per ampere. So radians is a dimensionless quantity, so we can throw it away. We have seconds in the numerator and seconds in the denominator, so those guys cancel each other out. So we have volts per amp. What's another name for a volt per amp? An ohm. So the units for the impedance of an inductor is also the ohm. Before we move along to capacitors, I want to bring your attention to something because I just have it dangling up here, but it is actually incredibly important, okay? So the impedance of a resistor, ZR, we found to be just R by itself. There is no dependence on omega whatsoever. So the resistor behaves like a resistor across all frequencies. The impedance of an inductor, however, is dependent on omega, right? We just figured out that it's J omega L. So at very low frequencies, let's say that omega is equal to 0, which would represent a DC case, what would the impedance of an inductor be? 0. How would we describe that? I think we would describe it as the inductor is behaving like a short circuit because its impedance is 0. So our frequency domain analysis exactly agrees with what we've already learned. What's really interesting, though, is that what happens when we get at very high frequencies? Our impedance is going up and up and up. So we have a frequency-dependent impedance here that at very low frequencies looks like a short circuit, and at very high frequencies effectively looks like an open circuit, okay? We can use that property of the frequency dependence of an inductance in order to develop what are called filter circuits, right? So effectively, it will reject all low frequency signals because the impedance is 0, and according to Ohm's law, the voltage drop across it will be 0. Or at very high frequencies, it will start to pass everything because as the impedance gets larger, all of the voltage drop will appear across the inductor if we just had a simple series circuit, right? So this simple concept of impedance that we're using in this class is actually the fundamental building block of filters that are used in control systems, power systems, communication systems, and all of this kind of stuff. Without inductors behaving this way, and as we'll see, capacitors behaving the way that they do, our cell phones and stuff like that literally could not exist. Okay, so just a very, very interesting little thing that's just implied here, and I just wanted to bring it to your attention of how important this concept of frequency dependency for these impedances are. Okay, rant over. So lastly here, let's talk about a capacitor. So for a capacitor, the ratio of phasor voltage to phasor current is going to come out to be what? 1 over j omega c. So in our capacitor, it looks like our impedance is inversely proportional to frequency, meaning that at DC, it looks like an open circuit, and at high frequencies, it looks like a short circuit. So we get the exact opposite filter response when we use a capacitor versus inductor. It tends to pass low frequency signals and reject high frequency signals. Okay, so in rectangular form, this looks like 0 minus j over omega c. Now, I'm sure some of you are seeing that negative sign and saying, where the hell did that come from? So let me explain that really quickly. I'm just going to sneak it in up here, right? So we have 1 over j omega c. If I multiplied both sides of this by, or the numerator and the denominator by j over j, what I wind up getting is a j in the numerator, an omega c in the denominator, and then I also have a j squared in the denominator. What's j squared? -1. So that's the same thing as negative j over omega c. And then lastly, we would have 1 over omega c with an angle of negative 90 degrees, like so. So we can make a couple of quick observations here. The impedance of a resistor is purely real. An inductor gives us positive reactance, and a capacitor gives us negative reactance. Okay. If we look at the units, we have 1 over radians per second. So I'm just going to do that as seconds per radian. And then I have the reciprocal of farads, where a farad was an amp second per volt. So I've just flipped that guy over. And if we look at our units, seconds cancel seconds, radians goes away, and once again, we have volts per amp or ohms. So impedances are all measured in ohms, which means we no longer have to have special rules for how to combine inductors, capacitors, and things like that. When we're dealing with impedances, just treat it like a resistor. So it does not matter what type of element it is. If it's a resistor, a capacitor, or inductor, treat it like a resistor, and sometimes it's imaginary. But it's just resistor combination techniques. Okay, I swear to God, I'm almost done yelling at you guys about this stuff. The last thing that I want us to do is to reanalyze that circuit from the beginning of class using what we've learned from today. Okay. So here's my circuit. Here's IS of T. Here's my 10 ohm resistor. Was this a 2 Henry inductance, if I'm remembering correctly? And then here is the voltage, Vs of T, that I was looking for. Okay. So we're not going to analyze this circuit in the time domain because I've showed you that's a terrible idea. Instead, we're going to analyze it in the frequency domain. So our process is going to be pretty straightforward. Oh, and let me tell you explicitly, Is of T is 3 cosine 8t plus 0 degrees amps. Okay. And we are looking for Vs of T. So what is the phasor representation of my current? So how do I take 3 cosine 8t plus 0 degrees from the time domain and convert it to the frequency domain? Keep the magnitude, keep the phase angle, throw the rest away. So what do I have? 3 angle 0. What's the impedance of my resistor going to be? It's just the resistor value itself. So the resistor does not change at all. So it was a 10 ohm resistor in our time domain circuit. It stays a 10 ohm resistor in our frequency domain circuit. What's the impedance of my inductor going to be? So the impedance of an inductor is j omega L. L was 2. What's omega? 8. Omega is the angular frequency of our sinusoidal excitation, 8 radians per second. So J times 2 times 8 is J 16 ohms. The voltage that we're looking for is this phasor voltage Vs. So using good old Ohm's law, Vs is 3 angle 0 degrees amps times 10 plus J 16 ohms, where I'm simply adding those two impedances together as if they were resistors. When I throw this into my calculator, I get 56.604 with an angle of 57.995 degrees volts, or the exact same answer we got an hour and 20 minutes ago using several pages of trig identities or several lines of complex number manipulation now just became Ohm's law. Complex numbers make our lives so much easier. Technically speaking, I'm not done because we were trying to find Vs of t in the time domain. So how do we go back from the phasor domain into the time domain? Keep our phase angle, or excuse me, keep our magnitude, 56.604. Throw back in our cosine omega t, and then introduce our phase angle. Done. Okay, so if I am remembering correctly, our next 2 class meetings are just effectively us analyzing circuits in the frequency domain. We have established all of the ground rules for everything that we're doing for the remainder of this class. So essentially what we get to do is just apply our DC circuit analysis techniques that we learned at the beginning of the class to these frequency domain circuits, and then take whatever result we get in the frequency domain and convert it back in the time domain. So my question for you all is, which of those DC circuit analysis techniques do you guys need a refresher on? Because we're not learning anything new for the next couple of days. It's just figuring out how to apply this stuff. Now, I will say, next Wednesday, I am going to talk about nodal and mesh in the frequency domain. That's really going to be more of a how to use MathCAD with complex numbers tutorial than anything. Because mesh analysis and nodal analysis in the frequency domain is the same damn thing as it was when we had our DC circuits. For what it's worth, your calculators literally cannot solve system of equations using complex numbers. So you're going to have to rely on techniques like current division, voltage division, KCL, KVL, source transformation, superposition, things like that in order to analyze any circuits on your exam. So which of those things do you guys not fully grasp or think you need a little bit help of remembering how they work? Tell me what to do on Monday. Current division, voltage division, okay. Superposition, okay. And then some source transformation. All right, so we'll work a couple of example problems, just kind of going over those rules again to clarify things. and then we'll hit up nodal and mesh on Wednesday, and then we'll get into our power relationships. All right, I'm done ranting for the day. Enjoy your next 11 minutes.